Service-neutral impedance problems can be classified as either slow-developing or sudden. Slow-developing problems gradually worsen over time due to factors such as corrosion, aging, or loose connections. Sudden problems occur abruptly due to events such as accidental damage, digging activities, or animal interference. Based on industry experience and anecdotal evidence from power companies, the approximate percentage of slow-developing versus sudden service-neutral impedance problems is as follows. Firstly, slow-developing problems are approximately 70 to 80%, and secondly, sudden problems are approximately 20 to 30%. This means that the majority of service-neutral impedance problems develop gradually over time, while a significant minority are sudden and unpredictable. This breakdown has implications for maintenance and inspection. Slow-developing problems may be detected through routine maintenance and inspections. Sudden problems are more difficult to predict and prevent. Slow-developing problems can be addressed proactively through repairs and upgrades. Sudden problems may require emergency repairs and can lead to service outages. Slow-developing problems may cause gradual voltage variations, while sudden problems can result in abrupt voltage changes or outages. Considering the nature of slow-developing service-neutral impedance problems, these issues typically manifest gradually over time. Factors contributing to this gradual development include, firstly, corrosion. Over time, metallic components within the service-neutral connection can corrode due to exposure to moisture, chemicals, or environmental factors. This corrosion increases the resistance of the connection, leading to higher impedance. Secondly, aging. Electrical components, including connectors and wiring, degrade over time due to thermal cycling, vibration, and other stresses. This aging process can loosen connections and increase impedance. Thirdly, loose connections. Vibrations, temperature changes, or improper installation can cause connections to loosen over time. Loose connections increase the resistance of the circuit, resulting in higher impedance in the neutral path. These slow-developing problems often present subtle symptoms initially, making early detection challenging. The gradual increase in impedance can lead to voltage imbalances, flickering lights, or erratic equipment operation. Regular inspections using thermal imaging or impedance testing can help identify these issues before they escalate into more significant problems. In contrast, sudden service-neutral impedance problems arise abruptly due to unforeseen events. Several factors can contribute to these sudden occurrences, including, firstly, accidental damage. Digging activities, construction work, or vehicle accidents can damage underground or overhead service-neutral conductors, causing immediate impedance changes. Secondly, digging activities. Excavation or trenching near underground electrical infrastructure can inadvertently sever or damage the service-neutral conductor, leading to a sudden open neutral condition. Thirdly, animal interference. Rodents, squirrels, or other animals can chew through insulation or damage connections, creating a sudden impedance change or open circuit. These sudden problems often result in immediate and noticeable symptoms, such as complete power outages, voltage surges, or equipment failure. Due to their unpredictable nature, preventing sudden service-neutral impedance problems can be difficult. However, implementing measures such as proper marking of underground utilities, regular vegetation management, and animal deterrence can help reduce the likelihood of these incidents. Understanding the implications of this breakdown between slow-developing and sudden problems is crucial for effective maintenance, mitigation, and customer impact management. For maintenance and inspection, slow-developing problems may be detected through routine maintenance and inspections, allowing for proactive repairs and upgrades. Techniques such as thermal scanning, insulation resistance testing, and neutral-to-earth voltage measurements can help identify areas with elevated impedance. Sudden problems, on the other hand, are more difficult to predict and prevent. These issues often require immediate response and troubleshooting to restore service quickly. Mitigation strategies differ depending on the nature of the problem. Slow-developing problems can be addressed proactively through repairs and upgrades. Replacing corroded connectors, tightening loose connections, or upgrading undersized conductors can help reduce impedance and improve service reliability. Sudden problems may require emergency repairs and can lead to service outages. In these cases, isolating the fault, replacing damaged components, and restoring power as quickly as possible are essential. From a customer impact perspective, slow developing problems may cause gradual voltage variations, flickering lights, or intermittent equipment malfunctions. These subtle symptoms can be frustrating for customers and may lead to premature equipment failure. Addressing these issues promptly can improve customer satisfaction and prevent more significant problems down the line. Sudden problems can result in abrupt voltage changes, power outages, or equipment damage. These events can disrupt business operations, causing inconvenience to residential customers and pose safety hazards. Effective communication, rapid response, and thorough troubleshooting are crucial for minimizing the impact of sudden service-neutral impedance problems. Regular maintenance and inspection programs play a critical role in preventing and mitigating service-neutral impedance problems. These programs should include visual inspections, thermal scanning, insulation resistance testing, and neutral-to-earth voltage measurements. By identifying and addressing potential issues before they escalate, utilities can improve service reliability, reduce customer outages, and enhance safety. In summary, service-neutral impedance problems can be either slow-developing or sudden, with slow-developing problems accounting for the majority of cases. Understanding the characteristics, causes, and implications of each type is essential for effective maintenance, mitigation, and customer impact management. By implementing proactive measures and responding promptly to unforeseen events, utilities can minimize the impact of service-neutral impedance problems and ensure reliable power delivery to their customers. From a technical standpoint, service-neutral impedance refers to the opposition to the flow of alternating current in the neutral conductor of an electrical service. This impedance can arise from various sources, including conductor resistance, inductive reactance, and capacitive reactance. High neutral impedance can lead to several undesirable effects such as voltage imbalances, harmonic distortion, and increased neutral-to-earth voltage. The National Electrical Code, NEC, provides guidelines for grounding and bonding to minimize neutral impedance and ensure electrical safety. Section 250.24 addresses service-neutral grounding and requires that the neutral conductor be grounded at the service entrance. This grounding provides a low-impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices. Section 250.4 outlines general requirements for grounding and bonding, emphasizing the importance of creating a low-impedance ground fault current path. Section 250.64 specifies requirements for grounding electrode conductors, which connect the grounding electrode to the service equipment. The size and material of the grounding electrode conductor must be adequate to carry the available fault current. Section 250.166 provides requirements for sizing the neutral conductor. The neutral conductor must be sized to carry the maximum unbalanced load. In some cases, the neutral conductor may need to be larger than the phase conductors to accommodate harmonic currents. Maintaining low neutral impedance is crucial for ensuring proper operation of sensitive electronic equipment. Voltage imbalances caused by high neutral impedance can lead to overheating, malfunction, and premature failure of electronic devices. Harmonic distortion can also interfere with the operation of electronic equipment, causing data errors, communication problems, and equipment instability. High neutral-to-earth voltage can create shock hazards and increase the risk of electrical fires. Regular testing and monitoring of neutral impedance are essential for identifying and addressing potential problems. Insulation resistance testing can help detect insulation degradation in the neutral conductor, which can lead to increased impedance. Neutral-to-earth voltage measurements can indicate the presence of excessive voltage on the neutral conductor, which may be caused by high neutral impedance. Thermal imaging can be used to identify hot spots in the neutral conductor, which may indicate loose connections or excessive current flow. Impedance testing can directly measure the impedance of the neutral conductor, providing a quantitative assessment of its condition. When troubleshooting service-neutral impedance problems, it is important to follow a systematic approach. Firstly, visually inspect the service entrance and neutral connections for any signs of corrosion, damage, or loose connections. Secondly, measure the neutral to earth voltage at various points in the electrical system. Excessive neutral to earth voltage indicates a problem with the neutral conductor or grounding system. Thirdly, perform insulation resistance testing on the neutral conductor to check for insulation degradation. Fourthly, use thermal imaging to identify any hot spots in the neutral conductor or connections. Fifthly, if possible, perform impedance testing to directly measure the impedance of the neutral conductor. Based on the findings of the troubleshooting process, take appropriate corrective actions. This may involve tightening loose connections, replacing corroded connectors, repairing damaged conductors, or upgrading the grounding system. In some cases, it may be necessary to install a dedicated neutral conductor to reduce neutral impedance. Proper grounding and bonding techniques are essential for minimizing neutral impedance and ensuring electrical safety. All metallic enclosures, conduits, and equipment must be properly bonded to the grounding system to provide a low impedance path for fault currents. Grounding electrodes must be installed in accordance with the NEC and should be regularly inspected to ensure their effectiveness. Surge protective devices, SPDs, can help protect sensitive electronic equipment from voltage surges caused by high neutral impedance. SPD should be installed at the service entrance and at critical load locations. Proper installation and maintenance of SPD are essential for their effective operation. Service neutral impedance is a critical parameter that affects the performance and safety of electrical systems. By understanding the causes, effects, and mitigation strategies for service neutral impedance problems, electrical professionals can ensure reliable power delivery and protect sensitive electronic equipment from damage. The NEC provides comprehensive guidelines for grounding and bonding to minimize neutral impedance and ensure electrical safety. Regular testing, monitoring, and maintenance are essential for identifying and addressing potential problems before they escalate. By following best practices and adhering to industry standards, electrical professionals can maintain low neutral impedance and provide safe and reliable electrical service to their customers. It's important to consider the impact of harmonics on neutral conductors. Nonlinear loads, such as electronic devices and LED lighting, generate harmonic currents that can flow in the neutral conductor. These harmonic currents can increase the neutral current and contribute to neutral voltage drop. The NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, including harmonic currents. In some cases, it may be necessary to install a larger neutral conductor or a dedicated neutral conductor to accommodate harmonic current. Harmonic filters can be used to reduce harmonic currents and improve power quality. These filters are typically installed at the service entrance or at individual loads that generate significant harmonic currents. Proper selection and installation of harmonic filters are essential for their effective operation. The use of shielded cables can also help reduce harmonic currents and improve power quality. Shielded cables provide a barrier against electromagnetic interference, which can contribute to harmonic distortion. Proper grounding of the cable shields is essential for their effective operation. Regular power quality monitoring can help identify harmonic problems and assess the effectiveness of mitigation measures. Power quality monitors can measure voltage, current, harmonic distortion, and other parameters that indicate the health of the electrical system. The data collected by power quality monitors can be used to identify trends, diagnose problems, and optimize system performance. In addition to the NEC, other industry standards and guidelines provide information on service neutral impedance and power quality. The Institute of Electrical and Electronics Engineers, IEE, publishes standards on power quality, grounding, and bonding. These standards provide detailed recommendations for minimizing neutral impedance and improving power quality. The National Fire Protection Association, NFPA, publishes the National Electrical Code, which contains requirements for electrical safety, including grounding and bonding. Following these standards and guidelines is essential for ensuring safe and reliable electrical service. The role of the utility company in maintaining service-neutral impedance is also important. Utility companies are responsible for providing a stable and reliable power supply to their customers. This includes maintaining the grounding system and ensuring that the neutral conductor is properly sized and connected. Utility companies may also perform regular inspections of the service entrance and grounding system to identify potential problems. Customers can also play a role in maintaining service-neutral impedance. By avoiding overloading circuits and using energy-efficient appliances, customers can reduce the amount of current flowing in the neutral conductor. Customers should also report any flickering lights, voltage variations, or other electrical problems to the utility company. Cooperation between customers and utility companies is essential for maintaining safe and reliable electrical service. Continuous education and training are essential for electrical professionals to stay up to date on the latest technologies and best practices for service-neutral impedance and power quality. Electrical professionals should attend seminars, workshops, and conferences to learn about new products, techniques, and regulations. They should also read industry publications and technical articles to stay informed about the latest developments in the field. By investing in education and training, electrical professionals can improve their skills and knowledge and provide better service to their customers. Service-neutral impedance is a complex topic with many different aspects. By understanding the causes, effects, and mitigation strategies for service-neutral impedance problems, electrical professionals can ensure reliable power delivery, protect sensitive electronic equipment from damage, and provide safe and reliable electrical service to their customers. Regular testing, monitoring, maintenance, and continuous education are essential for success in this field. Considering the slow-developing nature, the corrosion process impacting connections over time plays a significant role. Electrochemical corrosion occurs when two similar metals are in contact in the presence of an electrolyte, such as moisture. This creates a galvanic cell, where one metal acts as an anode and corrodes, while the other acts as a cathode. The rate of corrosion depends on the difference in electrochemical potential between the metals, the temperature, and the concentration of the electrolyte. To minimize electrochemical corrosion, use compatible metals for connections or apply a protective coating to the connection. Creep corrosion occurs when a thin layer of moisture or other contaminant is trapped between two surfaces that are in close contact. The contaminant can create a localized electrochemical cell leading to corrosion. Creep corrosion is often accelerated by vibration or thermal cycling. To minimize creep corrosion, use a sealant or lubricant to prevent moisture from entering the connection. Fretting corrosion occurs when two surfaces that are in contact are subjected to repeated relative motion. The motion can remove the protective oxide layer on the metal surface, exposing the underlying metal to corrosion. Fretting corrosion is often accelerated by high contact pressures and temperatures. To minimize fretting corrosion, use a lubricant or coating to reduce friction between the surfaces. Environmental factors, such as humidity, temperature, and exposure to chemicals, can also affect the rate of corrosion. High humidity can increase the rate of electrochemical corrosion. High temperatures can accelerate the rate of most corrosion processes. Exposure to chemicals, such as salt spray or industrial pollutants, can also increase the rate of corrosion. To minimize the effects of environmental factors, protect connections from exposure to moisture, chemicals, and extreme temperatures. Regular inspection and maintenance of connections are essential for detecting and preventing corrosion. Visual inspection can identify signs of corrosion, such as rust, discoloration, or pitting. Thermal imaging can detect hot spots caused by increased resistance due to corrosion. Electrical testing can measure the resistance of the connection to determine if it is within acceptable limits. When corrosion is detected, the connection should be cleaned and repaired or replaced. Cleaning can remove corrosion products and restore the original conductivity of the connection. Repair may involve tightening the connection or applying a protective coating. Replacement may be necessary if the connection is severely corroded. Proper installation techniques can also help prevent corrosion. Use the correct tools and procedures for making connections. Avoid over-tightening or under-tightening connections. Ensure that all connections are properly insulated and protected from moisture. Training of personnel on proper installation and maintenance techniques is essential for preventing corrosion. In addition to corrosion, other factors can contribute to the slow development of service-neutral impedance problems. Loose connections can increase the resistance of the circuit, leading to higher impedance in the neutral path. Loose connections can be caused by vibration, temperature changes, or improper installation. To prevent loose connections, use locking hardware or apply a thread locking compound to the connection. Over time, insulation can degrade due to exposure to heat, moisture, or chemicals. Degraded insulation can increase the leakage current in the neutral conductor, leading to higher impedance. To prevent insulation degradation, use high-quality insulation materials and protect the insulation from exposure to harsh environments. Electrical overloading can also contribute to the slow development of service-neutral impedance problems. Overloading a circuit can cause the conductors to overheat, leading to insulation degradation and increased resistance. To prevent overloading, ensure that circuits are properly sized and protected by overcurrent protective devices. Harmonic currents can also increase the neutral current and contribute to neutral voltage drop. Nonlinear loads, such as electronic devices and LED lighting, generate harmonic currents that can flow in the neutral conductor. To minimize the effects of harmonic currents, use harmonic filters or oversized neutral conductors. By addressing these factors, it is possible to minimize the slow development of service-neutral impedance problems and ensure reliable electrical service.